are now officially recording. We are live and in charge. We're going to be reviewing all the physics stuff that we covered in the first 6 weeks. I'd really rather not like to talk for the next 30 minutes straight, so if anyone has any questions, please feel free to ask them just now.
Is that supposed to be on the board, or?
That is supposed to be on the board.
That's really cool.
That's because I'm recording this entire screen, so that it'll send it to Loom so I can edit it and probably edit this part out because it's a little bit lame this one.
Is it not supposed to have a half a board? Because that's what I meant.
What do you mean?
Because like
Okay, well, it's also recording the entire screen.
Oh.
So this is just, so that people can see, hey, I'm a live person with a very prominent shiny bald spot, who's teaching me this physics here. So, any other questions? Okay, those are all good. You're doing it right, so give yourself a hand. That's fantastic. All right, so we started off the 6 weeks with math stuff. Okay, everybody's favorite things, sig figs, right? How much or how little do you want me to go back into the rules for sig figs? I imagine you will probably have at least a question involving sig figs, probably not more than 1 or 2 though. So do you want to hear it again? Clearly we don't want to talk about it, but we can, that's fine. Okay, so the rules for sig figs. First of all, the purpose of significant figures is taking some of the inaccuracy out of measured numbers and doing math with those measured numbers. So when you count sig figs, there's basically 4 or 5 rules you look at. Okay, first rule is if it's a non-zero, then it is significant. Okay, so we say yes on that. That's anything from 1 through 9. If it's a non-zero digit, we count it. If it is a sandwiched zero, let me put a little line on that. Are they significant or not?
No.
They totally are. Yes. Okay. So for example, if I've got something like 20.07, the 2 is significant and the 7 is significant because they're non-zeros, but these 2 zeros make up a zero sandwich, and now he looks like a scary clown. Okay. But both of those zeros, since they're sandwiched between non-zeros, we consider them as sig figs. If you have leading zeros, which are the zeros that are to the left of all of the non-zeros, are they significant?
No.
No. So for example, if I've got 0.0060, and these first 3 zeros right here are not significant. See, now he's angry. The 6 is because he's a non-zero, and this 0 is, we'll talk about why here in just a minute, because following zeros are they significant? Only if there's a decimal present. So if there's a decimal, then we say, yes, they're significant. If there's not a decimal, this is my not a decimal, then we say, no, they're not. Okay? So if I have 500, then the 5 is that these right here are not. If I take the same thing and I go 50.0, they're all significant. The 5 is, and then the other 2 zeros are to the right. Even if they're not to the right of the decimal, they are still considered significant because they are to the right of a non-zero while the decimal is present. Okay? And then the last rule is not really one you have to worry about that often. That has to do with counted numbers. Counted numbers are infinitely significant. You're not measuring them, you're counting them, so you are 100% sure of your significance there. Doing math with sig figs, if you're adding or subtracting, then you look at place value. And you have to go with your least precise measured number. So, calculator, for instance, if I am doing 17.45 plus 167 plus 400. First thing I do is I plug it into my calculator because even though I'm good at doing it in my head, I don't want to try this right now. 167 plus 400. The answer my calculator spits out is 584.45. Now I have to go back and I have to look at my numbers to find which one is the least precise. Which one is it? 400. It is only significant out to what place? The hundredth place. And so my answer has to be significant to the hundredth place. So I look to see what the next digit is to tell me if I round or not. Turns out I do. So I would report this as 600 with no decimal. Okay. When you're multiplying or dividing, then the rule is you count sig figs. And you go with the lowest number. So again, example would be if I have like 17.3 times 420. First thing I do is I pop it in my calculator, 17.3, almost 420. The answer that my calculator gives me is 7,266. Now I go back and I count sig figs. How many sig figs does this number here have?
3.
It has 3, all 3 of them. How about this one?
2.
It has 2. What's smaller, 2 or 3?
2.
I go with my lowest number 2, so my answer can only have 2. There's 1, there's 2. I look at my next digit to see if it's going to need rounding. It will. So I report this as 7,300. It has 2 sig figs in the answer. Pain in the drain, but there it is. And like I said, don't kill yourself if you don't quite get sig figs down now. That does not mean that you can't run for president one of these days. Okay, it'll pass. Using trig functions. Now, I will tell you that you are going to be allowed the use of your little cheat sheet that's got your trig functions on it if you got it tucked away in your calculator, and if you've lost yours and need another one by tomorrow, let me know and I can get you another one. That's fine. The big thing is just knowing how to use trig functions to find either a unknown angle or an unknown side. Does anyone need a refresher on how that looks, or do you feel okay with
That's
that?
the sine, cosine,
Sine, cosine, tangent, yes.
Why is it sine? That's funny.
I don't know. Sans is a little skeleton in a video game, I think. With the blue eye.
I think I know what game that's from.
My kid knows about that game. So, does anyone want to see some examples from that, or you feel good about just looking that up on your own if you need to? Okay. And we'll skip over trig functions. Interpreting graphs. In general, just kind of knowing how to look at a graph and know what it is it's trying to tell you, and what different trends in graphs tell you. We're going to look here in just a minute about some of the different motion graphs, and that'll get a little more specific. But in general, when you've got a graph and you're trying to determine, okay, what is my independent variable and what's my dependent variable, do you remember the little mnemonic device? Helps you remember which one goes on the X and which one goes on the Y. Ooh, cool. All right. The device you need to remember is dry mix. Remember this now?
Yes.
Okay. So your dependent variable goes on your y-axis, the one that you're measuring, the one that you're observing, the one that you're counting, whatever. The one that you are changing, the independent variable, goes on the x, the one you're manipulating. Okay? Responding variable, r, goes on the y. Manipulated variable goes on the x. So you can usually look at a graph, and if the person who made it knows what they're doing, then you can tell, hey, this thing down here is what they changed. Or like, if you're looking at something versus time, Time is not something you're measuring, right? Time is just happening while you're measuring something else. So in most cases, like if you're doing motion graphs, then time is going to be on your x-axis. Okay. Next slide is talking about motion in one dimension. So it's important to keep in mind the difference between scalars and vectors, like we just looked at on that last question. Scalars, excuse me. Scalars are quantities that are just numbers, just amounts. Vectors give those numbers direction. This is especially important because when we're talking about movement, when we're talking about forces that cause movement, forces that cause acceleration, those are vector forces. Those have direction. Just knowing the difference between some of these pairs of terms. So distance versus displacement. Okay, distance is literally the amount of space between 2 points. Displacement is directional. Okay, find displacement, you take your stopping point, you subtract your starting point, and you look at what direction you have traveled. Okay. Same sort of thing with speed versus velocity. Speed is a scalar. It's just distance divided by time. Velocity is distance divided by time, and also figuring in the direction that that thing has been traveling. We'll have another slide here in just a minute where we're going to talk about the different kinds of motion graphs, but it's important when you're looking at a motion graph to be able to recognize very, very quickly what kind of graph you're looking at, because if you think you're looking at a distance time graph and it's actually an acceleration time graph, then you're going to be reading a totally different story than whatever that graph is trying to tell you.
What is displacement?
Displacement, it's like distance, but it's distance in a direction. Okay, here, let's do an example on that. That's pretty good. Okay, so if I start at my starting point right here, and I move, so let's say that I start off at a certain point and I walk, let's say 4 meters east, and then I turn and I walk 3 meters north. Okay. The total distance I've traveled, I just take those, it's just going to be 4 plus 3, okay, so 7 meters. But if I want to look at my displacement is actually how far I have gone along a certain line vector, and it just so happens, because this is a 3, 4, 5 triangle, that I know that my displacement is equal to 5 meters, and it's going to be roughly northeast-ish. Okay? That's the difference between distance and displacement. Okay. If I'm on a track and I start off here and I run one entire lap, my distance is going to be however far I ran. My displacement is going to be 0.
Because you come back to the same spot.
If I end up in the same spot I started.
Okay.
Yeah. Good questions. And again, we'll look on the next few slides when we actually look at a few graphs here, what some of the different shapes and trends tell us on each of these types of motion graphs. Big thing about positive versus negative, remember, we're talking direction. We're not talking, negative numbers. We're talking, if it's positive, it's whatever direction we define as positive. If it's negative, it's whatever direction we define as negative. Acceleration due to gravity is constant for an object in free fall if you take all other forces out of the equation. Okay, if you take out of the equation, air resistance would be the biggest one. If I drop a bowling ball and a feather at the same time, the bowling ball is obviously going to fall and hit my foot before the feather ever does, right? Because the feather is floating down on air. You take a bowling ball and a feather and you put them in a vacuum and you drop them, they will fall and hit the ground at the same time. Because there's no wind force vector acting in the opposite direction from gravity. Okay, if it's in free fall, then it's constant acceleration while it's in the air. So here we've got our 3 graphs that we've seen before: position time, velocity time, acceleration time. And actually, it just so happens that all 3 of these graphs are telling us the same story. So let's look at these shapes and see what they can tell us, okay? On a position versus time graph, if you have a chunk where you've got a constant line, what is that telling you about the object that you're looking at? Okay, it's in a constant state of motion. Exactly right. It's not getting faster or slower. If it is a line with any kind of positive or negative slope, then it means that it is moving at a constant velocity. Okay? If you have a portion where you've got a curve, so like if we look at this portion right here, from here through here, what's happening here is that it is changing velocity, right? Okay? So here we have acceleration going on. And I would say that if I was just to trace this starting here at the start, then it is in motion, moving away, and then it slows down, it starts coming back. It walks back past where it already was in the opposite direction. It's moving away, and then it begins slowing down, and then it starts coming back toward where it was. At this point, it's reached its original position. Now it is continuing to move away from that starting position at a constant rate. Go back, you jerk. Where'd you go? Okay, there we go. Switching our focus over to a velocity versus time graph. You see the places where this is curvy? On the position time graph are the same places where it's straight lines on the velocity versus time graph. Okay? So if you've got a straight line on a velocity time graph, like, this chunk right here, this doesn't mean you've got a constant velocity, it means that you have constant acceleration. Okay? So I have positive velocity to start off with. What kind of acceleration am I exhibiting between here and here? Is it positive or negative? It's negative acceleration. You can tell that because this line on the velocity thing has to do with negative slope. You know what? What would be a good idea for us to put some keys up? So for position versus time, slope equals velocity. On a velocity versus time, our slope equals acceleration. So, from this point here up to this point here, looking at the second leg of things, okay, which is happening from this time chunk to this time chunk, so it's happening between here and here on this, what kind of acceleration is it exhibiting? Positive acceleration. And then when we get to this next little time chunk starting right here, up through here, so this time to this time, it's also positive acceleration, but tell me, how does this acceleration here compare to the acceleration there?
It's slow.
It's slower. So like you're smashing the gas right here, and then you kind of let off the gas, but you're still giving it some, right?
Yeah.
And then when you get to this chunk of time right here, constant velocity, right?
Yes.
Okay, so let's put that down. So that's constant velocity. Okay, there is no acceleration. Zero slope, zero acceleration. We're not getting faster, not getting slower. So during that time chunk, and actually on here, it would be between here and right here, moving at a constant rate. Which is great, because if we jump over to our last graph, so this time interval, let me see if I can just kind of highlight it in greenish, okay? So this time interval here, from this point here to this point here, is the same as this time interval here, from this point to this point. That's the same as this time interval here, from this point to this point. You see how they're all connected? If our very last graph is measuring acceleration, we have to look at this one in a slightly different way, okay? If you are on the zero line, then you are not accelerating. I think I spelled that right. Okay. So if you have zero acceleration, it means your velocity is constant. Now it might mean that you're being still. You might have a constant velocity of 0. Or it might mean that you've got a constant positive or negative velocity. You can't tell just by looking at this kind of graph. All that this graph looks at is change in velocity. Okay? The farther you are from the 0 line, you're having more change. Also down here, you're having more change. Just because this is above 0, this positive change, that means it's moving in the positive direction. So a force is applying you in whatever direction you've designated as positive. If it's down here, the more change is in the negative direction. So whichever way you've designated as negative, you are being accelerated that way. So if you look here, check out how in this time segment here, you've got negative acceleration. Well, in that same time segment, look, sure enough, there's your negative acceleration. In this chunk right here, you've got positive acceleration. And sure enough, right there, that acceleration is positive. Now, you told me that this one right here versus this one right here, that x, our acceleration is changing faster than it is in y. Well, this would seem to agree with you. Here it is during segment x. Here it is during segment y. You're still positive acceleration. It's just not as much. Okay? You see how they're all tied together and how, I know it's a lot to keep track of, but what you really kind of have to do is really just break it down a piece at a time. Again, I think it comes in really handy as that next slide, but let me see. And we're back to our cheetah graph again. Okay? This is like our cheetah sheets. So, again, 3 different types of graph, what they're showing you with each one. Okay, a flat line for position demonstrates that you're at a constant position, you're not moving. You have 0 velocity, you have 0 acceleration, and your velocity is not changing from 0. If you're at a constant velocity, you've got a positive slope or a negative slope. If it is a line like this, and not a curve, it means that your velocity is going to be a straight flat line. It's not going to be on 0 anymore though. It's either going to be positive or negative depending on the direction that you're moving. This is above the line, so you're moving in a positive direction. Since it's constant, again, there's 0 acceleration. You're not changing your speed during that interval. And then again, the final one, if I'm under constant acceleration, then I have a curve on this first one. I am moving faster and faster and faster and faster, which means that my velocity graph is increasing at a constant rate, which means, hey, now I do have constant acceleration.